All right, so good day, one and all. This will be part 3 of the video on aromatic compounds. Then in this video, we are focusing on the effects of substituents, right? So the effect of substituents on substitution reaction. Very simple. Good. So now we are saying that there are two main effects of substituent. The first one is that substituents will affect the reactivity of the aromatic ring. So the compound's reactivity will be changed by the substituent. The next thing is that substituent can direct the incoming substitution. So if I have a substituent and then another atom or group of atoms are coming, the substituent there can affect the position of substitution. Very simple. So we'll take them one after the other. The first point here is reactivity of aromatic ring. So we are saying that we have substituents that we call activating substituents. Now they make the aromatic ring more reactive. These examples are supposed to be kept. So the first one they are giving us here is the amino functional group, right? Good. Then we have the OH, the hydroxyl group. Then we have the methoxy group, right? Good. Now these groups are the activating group. There's a trick that we used to keep, even though it doesn't work for everything, that if we have the electronegative atoms, nitrogen and oxygen directly attached to the ring, right? And usually you are having something like an activating group. But then you realize that there are exception like nitro and then this quaternary ammonium substituent. And so it doesn't really work. So it's good you keep the examples in your head. So these are activating group. We'll discover more with time, right? Then we have other substituents that we call deactivating substituents. They render the aromatic ring less reactive. Examples worth keeping, we have this is the aldehyde functional group, nitro. This is carboxylic acid, right? Good. This is an ester, this is a quaternary ammonium. These are all deactivating groups. So once this is on any ring, it makes the aromatic ring less reactive. Very simple. Good. And so you realize that if you are comparing, assuming the reactivity of benzene is 1, right? If you compare benzene to phenol, which has OH on it, it is 1,000 times faster. So that means the reactivity has been enhanced by this substituent. Now, if you compare that to nitrobenzene, right? Now that's a lot slower. So 6 times 10 raised to the power -8, very slow. And that shows the effect of substituents on reactivity. Very simple. Good. Now, the next one, we are seeing that substituents influence the orientation of the reaction by either auto-para-directors or meta-directors. So from this, you realize that if a substituent is moving you to the auto direction, it is automatic that you also get to para. So it's, even though we'll have major and minor, auto and para-directors are put under one category and meta-directors are also put under a different category. Very simple. Now the continuation, they are saying that hydroxyl group and amino groups are auto-para-directors, worth keeping. So we should take note of that. Now we are saying that while substituents such as the aldehyde functional group and the nitro group are meta-directors. Good. That means if a new substituent is coming and then we have a nitro group on the benzene already, it will move it to the meta direction. Now, it is worth mentioning here that if the substituent assumes a position 1, para is 1,4. Good. Meta is 1,3 and O2 is 1,2, right? So let's keep those things in mind. Very simple. Now we are saying generally, substituent can be classified into auto-para-directing activators. So activator will be in terms of reactivity. So we have some substituent that will activate the ring and direct them to the auto-para direction. Then we have auto-para deactivators. So even though they are moving you to the auto and para direction, they are deactivating that. We realize some of them with time, right? Then we have meta directing deactivators. So something like nitro, the NO2 group is a meta-directing deactivator. If you take the halogens, they are deactivating the ring anyways, but they are auto para-directors, right? And then if you take something like the hydroxyl group, the OH group, now it will become an auto para-directing activator. It is activating the ring and it's directing the substituent towards the auto and para direction. So that is it generally. So we can categorize them here. So every other thing we'll talk about will fit into one of these three sets, these three broad classification. Now we are seeing that electron donation or electron withdrawal ability of substituents is controlled by the interaction between inductive and resonance effect. So sometimes the effect of the substituent will be due to inductive, whether positive or negative, right? Or resonance, also called mesomeric effect. And then we'll talk about that when we start with specific examples. Good. So specific example, the first one, electrophilic substitution on phenols. Good. Now, we have already said that hydroxyl group is an activator. So we realize that phenol is a lot of time more reactive than benzene. So we are seeing benzene reacts with bromine only in the presence of Lewis acid. That's on a normal day. Benzene will react with bromine in the presence of Lewis acid, right? But then when you're talking about phenol, you don't even need any catalyst, right? And then it will be so rapid. So we are seeing phenol reacts rapidly, 3 times faster without a catalyst, right? With bromine to form. Now, it's not forming a monobrominated product. It is forming a tribrominated product. Very important, right? So we want to just prove that it is so reactive. The reactivity has been enhanced that we don't need a catalyst. Even without a catalyst, it is faster than when it was a catalyst for normal benzene. And then even without that, we are getting a tribrominated compound. Even the first one was given as just monobromination, right? And then it occurs at specific positions. So this is a reaction to show what has happened. We have bromine liquid in ethanol and water, right? Mixture of ethanol and water. Now, when we put the phenol in, realize that we get tribrominated something. Very reactive, very reactive. Very active. Good. Now we are saying that the substitution at specific position, it is not random. It is not by a random chance that the bromine is on the O2 position and the para positions. No. The O here, the oxygen here has lone pairs. We call it the non-bonding electron. Now that non-bonding electron will contribute to the pi system of electrons. So the pi system of electron here would be enhanced. The electron density will be enhanced by the lone pairs here. Now, the enhancement occurs at specific locations in the ring. Those specific locations are the auto and para positions. That is why the substitution occurs on the auto and para positions. So this is structures to illustrate how it happens. Now, we have the lone pair of the oxygen being contributed to this carbon here. Now, it would, because of the formation of this new bond, right? The bond here between these carbon will break onto this carbon. Now, when it happens, we get our first resonance structure, right? So this is a resonance structure, this is a resonance, so canonical. Good. Now, you realize that there are a lot of electrons deposited on the auto position. Now, electrons on the carbon make carbon very unstable, so it would also be deposited on the next one. So it would move it here, and when it comes here, the pi bond breaks onto this carbon. When the pi bond breaks onto this carbon, realize the electron density here would also increase. But then this is highly unstable, right? Good. And so what will happen here is that the electrons will be contributed to the next carbon here, and the pi bond will break onto the last carbon atom here. Now, when it breaks here, right, realize that the electrons will be here, increasing the electron density at another auto position before finally we have it breaking back to the original carbon, and then the bond between the oxygen and carbon breaking to neutralize the positive charge. Now, this stabilization or this contribution will increase the electron density at the auto and para position. So it is no surprise that when we brominated, we had the substitutions at the auto and para position. Very important. Now, we are seeing that phenol is very reactive, right? But sometimes, and then it can lead to tribromination on a normal day or under normal circumstance. Sometimes we desire mono substitution. And so this point is saying that for mono substitution of phenol, we require a very low temperature, that is below 5 degrees. Now, these conditions are very important. Below 5 degrees, and they require one equivalent of bromine and carbon disulfide. So we don't have to use excess bromine if you want to achieve monobromination. So one equivalent of bromine, and then we are using a non-polar base, highly non-polar base. That's non-polar solvent, sorry. So carbon disulfide as a solvent, right? Now we are saying the major product here will be a para product, and then the minor product will be what? An auto product. Very simple. Good. Now, these structures is explaining to us why, okay, sorry, so I jumped the slide. Good. So these ones will explain to us why para is the major product. That's why para is the most stable. Now, generally, para is the most stable because it has more resonance structures. Even without drawing, you realize that this is the first step. Now, this is the intermediate carbocation form. It has 4 different resonance structures. Now, if it were to be meta position, right, after the first step, you realize that we'll have 3 different resonance structures. Now we have a saying that the more the resonance structure, the more stable the compound. And so the one producing more resonance structure automatically will be the more stable, and that's what will be favored. And so always the substitution occurs either on the para or on the O2 because they have 4 resonance structures, and then the meta will not occur because it has 3 resonance structures and then highly unstable intermediate. Very simple. So that's what this point is saying. We can learn how to draw the O2 position here. The positive charge will be here because this bond was being shared between this carbon and this carbon, right? Good. Now delocalization. So the bond here will break. So it will be shared between this and this. Then the plus sign will be here. Now there's a red around this because this is where the catch is. That's the delocalization occurs such that the cation falls on the carbon bearing the OH. Now, once that happens, what will happen is that it will give the opportunity to the O to contribute its lone pair to stabilize the positive charge. So that's what has happened here, that the O would also use this lone pair, contribute and stabilize. Now, once O is contributing to the stability of the intermediate, it increases the stability generally, right? But so the next step, we have it breaking back the electrons from the oxygen breaking back, right, to the oxygen, and then the next pi bond breaking to stabilize that one. A new positive charge is formed before we have the base abstracting, right? And then we are saying para because of more resonance structure. Very simple. If you come here, there's no opportunity for the positive charge land on the carbon bearing the OH. So we don't give the OH the opportunity to contribute. That is if it's meta. And so hardly would it be meta or never would it be meta. Very simple. Good. Next point. Okay, so there was a point I didn't read, very important to note, that we are saying that for the conditions that we use to monobrominate, if it's chlorine, you will still get trichlorinated phenol. Very simple. Very important to note. Good. So multiple chlorination of phenoxyacetic acid also lead to formation of 2,4-dichlorophenolxyacetic acid. So this is phenoxyacetic acid. We first add chlorine. Now it will give you para, right? Most preferentially. Now it's giving you para because the O2 positions are quite occupied. They are quite bulky, right? So para is free and then you give you para. So because of steric hindrance, right, or special hindrance. Now even upon the next chlorination, you realize that the chlorine was substituted on only one O2 position, which is quite free. The next O2 position is unsubstituted. Very important. So you realize that there's only one O2 position occupied because of a steric hindrance or special hindrance. Very simple. Very simple. And this one you can use your eyes to even see. Good. Nitration of phenol. Now we are seeing that nitration of phenol is problematic under normal nitration conditions since concentrated nitric acid oxidizes phenol. So we use dilute instead. right? The first instance we're doing nitration in regards to normal benzene, we have to get concentrated HNO3 and H2SO4. And that would have given us the nitronium ion before the reaction could have been initiated. In this instance, we are saying if you use the concentrated ones, right, it will oxidize the phenol. That's not what we want to happen. So we use dilute ones. And then we thank God that in this case, the phenol's reactivity has been enhanced, else this reaction couldn't have been effected. Very important to note. Now, so we have it, right? Dilute, and then we are forming our nitro phenol, right? Now check the percentages available. You realize that unlike the usual ones, right, the auto product is the major product and the para product is the minor product. Now, the explanation to this is what has been circled in red here: intramolecular hydrogen bonding. Now, I realize that hydrogen bonding always occurs between a polar hydrogen and lone pairs, right? Good. Now, this hydrogen is very polar because it's bonded to oxygen, of course. Now, there's an oxygen here with lone pairs. Very simple. And so there will be this reaction, right? That connection, that not reaction, that connection. Now, this intramolecular hydrogen bond will stabilize the the auto product. Now, once that auto product is stabilized, right? I always say that reaction proceeds to form more stable products. It proceeds to form more stable products. And so once that is more stabilized, it will be the major product. Very simple. Very simple. Good. How to prepare paracetamol? I feel as pharmacists, when we get to areas like this, we become happy because we know what we are learning is practical. And then from now on, if we ask you to produce paracetamol on a book, you can do it. Right? Good. So in the book, now we are starting from, at the end of the whole discussion, you can start from benzene, but now we are starting from paranitrophenol, right? Good. Now, what are we doing first? We are reducing the nitro group to aniline. Very simple. Good. Then we'll put acetic acid anhydride, right, to get our paracetamol. Very simple. No two ways about that. Good. Now, how to prepare aspirin? Very important too. So, as a pharmacist, this should also make you happy because at this point, on paper, you can produce aspirin, and then we are starting from phenol. Now, in order to produce aspirin, we convert the phenol to a more reactive product. That is phenoxide ion. The phenoxide ion is more reactive than phenol. And then we use this to do. So we use NaOH to convert the phenol. That's we use it to deprotonate the phenol to the phenoxide ion, which is more reactive. Then we add carbon dioxide, right? Before we come and acidify, right? Good. After acidifying, we get our salicylic acid, right? Salicylic acid. Good. Then there we add our acetic acid anhydride, right, to form our ester up here. And then we get our acetyl salicylic acid, also known as aspirin. Very simple. Good. Now these things you should practice them so that you have them off head. Very simple. Good. Now we are done with phenol. We are coming to aniline. It might interest you to know that aniline is more reactive. Now it is more reactive than phenol. That's towards electrophilic substitution. It is also more reactive than phenoxide ion. And it is also more reactive than phenyl ether. Now, it will interest you to know that aniline reacts vigorously with bromine to give you thiobrominated products. Now, it would interest you to know that under the conditions where phenol will give monobrominated products, when you give the same conditions to aniline, you will still get tribrominated product. And that is what has been illustrated here. If I am giving these conditions, bromine in carbon disulfide, temperature less than 5 degrees, I am getting just mono if it's phenol. But if it's aniline, it is very interesting to note that you will still get tribrominated products. And then the explanation here is because of the electronegativity of these two that we are talking about. Phenol has oxygen, right? Now, aniline has nitrogen electronegativity, right? Now I know as a pharmacist, you know. So you know that oxygen is more electronegative than what? Nitrogen, right? And so if you are talking about donating your lone pair of electrons, right, it is easier for aniline to donate because the nitrogen is less electronegative. It is easier for it to donate to increase the electron density around the ring, around specific areas in the ring, than how oxygen will be able to donate, right? So the low electronegativity of nitrogen in aniline makes it easier for it to donate its lone pair to increase the electron density in the ring, right? And then hence more reactive. Very simple. Very simple. Good. Good. So we are saying that in order to monobrominate aniline, now what we do is that we would reduce the interaction of the lone pair, right? And then how do we do so? Let me just read through this one. Very simple. So aniline can be made less reactive by preventing strong interaction of the nitrogen lone pair with the pi system. Now, this is done by acylating the imine into an amide. So we need an acetic acid anhydride to convert the imine to an amide. Now, when you do that, there's something interesting that I'll tell you about. Very, very interesting. But let's finish this. We are seeing that the amide nitrogen activates the benzene ring weakly. We'll talk about why it activates weakly, leading to a more controlled substitution reaction. After bromination, the amide can only be hydrolyzed. Sorry, after doing our monobromination, we can hydrolyze that amide bond using aqueous acid to get our normal amine back. So that is what has been illustrated here. Now, in the first instance, you realize that the aniline, we added acetic acid anhydride to convert it to amide. After converting it to amide, then we are showing you how the availability of the lone pair is reduced because the lone pairs on the amide, the nitrogen, it is used in the resonance stabilization of the amide itself. Now, because it is used in the stabilization of the amide, it is less available to be used in increasing the electron density in the ring. So it's like, now if it's available and it has no work, it would be used to increase the electron density around the ring. Now we have given it a different work. So its attention will be drawn a little bit towards the second work. And then its efficiency in enhancing the reactivity of the ring will be reduced. So that's what we did here. Very simple, right? Good. Now in this case, if we put bromine there under normal circumstances, we can get our monobrominated product. And after that, we can use acid to break this amide bond to get our monobrominated aniline. Very necessary. Selectivity between O2 and para, between O2 para positions. So why would one prefer O2? Why would one prefer para? Even though they move together, at a point there's preference for one of them. Now the first one says that steric effects tend to favor para substitution as occurs in bromination of amide. So you realize there was one example where, okay, let me try and go back and refer us to where the mono. Good. So you realize that in this, because of steric hindrance, para was favored first. So para will be the major because of steric hindrance, obviously. Good. Good. And then in most amide bromination, you realize that para is favored because of steric. The amide group is a very bulky group. So para is favored. Now, inductive electron withdrawing effect of electronegative substituents such as oxygen and nitrogen, this favors para. So there are some atoms like oxygen and nitrogen, right? They will withdraw, that's because of their inductive, they will withdraw electrons from the ring, right? But then they can also contribute electrons to the ring through resonance effect. So if we have oxygen directly attached to the ring, if we have nitrogen directly attached to the ring, what happens is that there are two effects occurring at the same time. The oxygen, because it's highly electronegative, will withdraw electrons from the ring through inductive effect. And the same oxygen will also increase the electron density in the ring. That's the pi electron density in the ring through that resonance. right? Through resonance. And we are saying that these ones favor the para. So oxygen and nitrogen will favor para positions, right? Now we are saying these atoms increase electron density of pi electrons by resonance, but withdraws electrons from the sigma bond by negative inductive effect, affecting mostly the nearest one. So the nearest ones are not favored because even though we are increasing electron density at those points, there's still the factor of deactivation, because of the inductive effect. And the one which is least affected in every inductive effect is the one which is furthest away. The one which is furthest away, and usually is the para position. Very simple and very understandable. The auto substitution can be favored when there is a coordination to cation, as occurs in synthesis of auto salicylic acid. So in salicylic acid, you realize that there was a negative charge, right? Now, even though we didn't show it here, but then it doesn't negate the fact that there's a cation. Usually, you have something like sodium, Na plus in the medium coordinated to this one. Right now, that coordination will help the auto become the medial product. So that's one thing that favors the auto being the medial product. We'll talk about another one as we go along the slide. Very simple. Good. Now, alkyl benzene, we are seeing the notes. Alkyl benzenes, that's alkyl groups on benzene or arenes, are also auto paradirectors. That's by positive inductive effect or hyperconjugation. Take note of these two words. So positive inductive effect or hyperconjugation. Right. Good. Now, alkyl groups like they can also activate the ring. They can activate the ring. Now, they activate by we call them electron showering or electron sharing. They push their electrons through the sigma bonds, right? And so you realize that it is activating in the auto para direction, but the auto is favored because we are working in sigma bonds. The auto will be the first affected. So the electron density increase at these auto positions are higher than that which is increased at the para positions. And so always realize that auto position is favored. So there's another thing that favors the auto position, right? So auto 60%, para 35%, and then sometimes you get more of meta positions because it is actually positive inductive effect. Good. Sulfonation of toluene. That's the alkyl group, right? Or alkyl benzene arene. Now we are saying that sulfonation of toluene with conc A2SO4 leads to the formation of auto and parasulfonic acids. This is no surprise because we have already said that alkyl substitution on benzene are auto paradirectors, so nobody should be surprised here. The next statement, p-toluene sulfonic acid can be isolated as sodium salts. Very important. I will explain. The next thing which is here is that para-toluene sulfonic acid is a solid acid, useful as a convenient strong acid. Now, we've used strong acid. This one was part of the lab. You can go and check your labs too. And I think another solid acid that we use is sulfamic acid. So he will talk about solid acids when he gets here. Right? So try and show him that in the lab you are using a solid acid, which is sulfamic acid as a primary standard. Very simple. But let's look at what's happening here. We have the toluene. Right? This is the toluene, conc A2SO4. Now we have two products, right? We have the auto product and the para product. Now, when you add the NaCl, it is only the para that will react, and that will help us isolate. That will explain the second point that p-toluene sulfonic acid can be isolated as sodium salt, and so it will help us isolate this one. Now, when you isolate this one, you can acidify it to get back our sulfonic acid functional group, right? And this is an important catalyst, very important. So that's just one of the importance. The next thing is that it is also a good leaving group in SN2 reactions. SN2 reactions. And then in SN2 reaction, the one that we use is the tosyl chloride, and this is the tosyl chloride. The para-toluene sulfonyl chloride is this one. This is O2, right? This is the para one, the lower product. And then it's a good leaving group in SN2 reaction. Good. And so what we're talking about were activators, autoparadirectors. Now let's talk about electrophilic substitution on benzene bearing electron withdrawing substituent. So we've already mentioned some example of electron withdrawing substitution like nitro groups and all. Good. Now we are seeing nitration of phenyl trimethylammonium leaves mainly to meta products, so deactivators. Now, they are meta directors, right? Most of them, that's the one we are talking about. So a specific example like phenyl trimethylammonium. Now, the trimethylammonium is the deactivating group. The trimethylammonium is the deactivating group on it, right? Now, the rate determining step, the rate is slower, so it's a deactivator. So it's approximately 10 raised to the power 7 times slower than nitration of normal benzene, right? Good. Now, nitration of this is also a meta product. So this is trifluoromethylbenzene. This is a deactivating product. Very simple, right? Good. And then we are saying they are meta directors, so we can just take note of them. Meta directors. So deactivation, meta direction. Meta directors. Very simple. Now I realize that between these two, what will happen is that this is a stronger meta director and a stronger deactivator. So, and then there's no surprise. I mean, this is methyl group on nitrogen, right? So there's no electron for donation and all because all the methyl groups have been exhausted. I mean, nitrogen has formed 4 bonds, right? Good. But then methyl groups are a little bit electron sharing. So even the deactivating ability of the nitrogen is reduced a little bit. Now, when you come here, the fluorine here is highly electronegative. So it will make this carbon very polar. And that carbon will also withdraw electrons here, right? Through inductive effect. So you realize that the effect on this ring is high. So the deactivating effect here is actually very high than in this case, right? Because the fluorine, the 3 fluorine are enhancing the deactivation activity of the whole substituent on the benzene ring. Very important to note. Now, why is metal substitution favored when we are talking about deactivation? Metal substitution. So let me note here that the deactivation that we are talking about here is also inductive effect, but it's not always. So these two, this is inductive effect. This one is inductive effect. Very important to note, inductive effect. Now this one is conjugation, so this is resonance, right? So we'll talk about that. So the two different scenarios would be in place. But why? Why meta substitution? Why meta substitution? So we are showing meta substitution. It has 4 resonance structures. Now, we also showed auto substitution here, and it also has 4 resonance structure. That means we cannot use the number of resonance structures to explain. Now, what can we use? Look at where the positive charge is. Now, note where the deactivating group is. You realize that throughout the resonance of this, there was no part where the positive charge fell directly under the deactivating group. But then when you come to the auto or the para substitution, you realize that at the point within the intermediate stabilization, the positive charge will fall directly under the deactivating group. Now, come to think of it, the substituent is withdrawing electrons, right, and then deactivating the ring, so reducing the extent or the availability of electrons in the ring. And we have put a positive charge on that same carbon. This will make the compound unreasonably unstable. That's English. And because of that, this would not form. So this would not form at all. This intermediate will not form at all. It's a no-go area. And so always we prefer meta substitution or meta substitution product will occur because of this intermediate form if you go auto or para. Good. So how electrons are withdrawn by conjugation has also been shown. We can go through the resonance structures. So you realize that the bond between the oxygen and carbon, the pi bond can break onto the oxygen, and that would make the carbon go in for electrons. So the pi bond in the ring would break and then try and stabilize the carbon here, right? Try and stabilize the carbon here because it's also losing, right? Now, when it breaks like that, there will be a positive initiated in the ring, and then subsequent delocalization around the ring stabilizing. So this positive charge induced by this substituent reduce the availability of electrons and deactivates the ring. And this is conjugation, right? Resonance. This is not inductive effect, resonance. Good. Now, the next thing we are talking about is the effect of halogens on benzene. Effect of halogens on benzene. So we are seeing that all halobenzenes react more slowly. They are deactivators. If there's a halogen on the benzene ring, it's a deactivator. But then it's also an autoparadirector. It's a deactivator and autoparadirector. So it's worth noting. They are deactivators and autoparadirectors. Good. Next up, how substituents may cooperate or compete. So sometimes, depending on the position of different substituents, they might cooperate to put the incoming substituent at a particular position, or they might compete, and one of them will win, right? And then get the substituent at the position that it wants it to be. So we'll talk about the different scenario. Now, this first example, that's so they are saying that two or more substituents can cooperate or compete in their directing effect. The preparation of bromoxynil, right? It's a herbicide, right? That now, if you look at this reaction, what's happening is that we have this is a meta director here, and this is what auto para director. Now the para position is occupied, so we can't even talk about it again. It's not available. So we are talking about this one being meta, this one being auto. Now if you look at it very well, the meta for this one is this position, these two positions. Now that is the positions, or these are the positions which are also auto to the phenol. And so both of them will cooperate and put the bromine at this point. You cooperate and put the bromine there, and that's what we call cooperation. Let's look at the next example. That we see competition. So before we can decide, we should know the effect of the substituents already. So what's happening here? Now we have this phenol. Now phenol is autopara. The para has been occupied, so we can't even talk about it. But this is the auto of the phenol. Auto. Now the alkyl group is also an autopara director, right? And this is its auto position. Wow, so there's war now. So the two have to compete. You are doing Friedel-Crafts alkylation, and then now these two have to compete and see where the substituent can come. Now, because this is a stronger director, right? It would win the competition, and then we'll come and put it at its auto position. So the incoming substituent will be at its auto position. That's what we call competition. In order to understand competition, you should know the direction of the substituents and then their relative strength. Now, in the next instance where we are still brominating it, it's still one, the phenol still one, that's the hydroxyl group still one, and then brought the substituent at its auto position. Very important. So this is competition, not cooperation. Good. Next up. Good. So a question for us. Now we are saying that we are brominating this, we are doing monobromination of this. So where would the product go to? Now this question, the compounds are the same. We have two equal compounds, right? Yes, they are all imides. So there's an imide on top, and down there, what do we have? We have CH3, that's a methyl group. But then it's still different. The compounds are the same, but different. Good. Now I realize that at this point, what is happening here? The nitrogen is directly bonded to the ring. So the electrons are here to be donated, right? But then its availability is reduced a little bit because of, obviously, the imide here, right? So it's used in stabilization, but it is still there. So the substituent here is what? Is an auto-para director. So we are focusing on its auto position because the para is occupied. Now, this one too is an auto-para director. So if you are brominating, the aniline will win. Sorry, the imide group here will win, of course, and then the bromine group will be here. Very simple. Good. This is a proposed answer. Good. Now, in the next instance here too, what's happening here is that we have the carbon directly bonded to the ring. Right? Now, carbon has no lone pairs to activate. So this whole group here is now a deactivating group. And then the direction here will be what? Will be meta. So it is meta, right? And then what will happen here is that this one too is directing to the auto and para. This is its auto position, this is auto position, right? Good. So very simple, they will cooperate and put the bromine at one auto position. And so whilst this one happening here is competition, This one is what? Cooperation. Very simple. Good. Now, I think that's next up. We have nucleophilic reaction, which will be captured in a different video. So and yeah, as I always say, if you have any question, see any member of the GPSC academic board. Thank you very much.